Good morning, dear students. In the last video, we were discussing about signal flow graph, how to arrive at the transfer function using Mason's gain formula. In this lecture, what we will be learning is how to draw a signal flow graph from a given block diagram. Okay. So here we have a block diagram and we have to now write the signal flow graph. Once we have a signal flow graph, then we apply Mason's gain formula and we will fill up all the variables which we have to find out or which we have to use it in that equation. We will substitute and we'll get the transfer function. Okay. So here, if the block diagram is given, we have to convert that to signal flow graph. For that, we have to identify how many nodes we require and how many branches, how many connecting branches. So how many nodes, that's a very important parameter. So here, number of nodes is equal to the number of input, number of output, number of summer used, and number of takeoff points. I repeat, how many nodes you will be having in a signal flow graph. So for a given block diagram, you will be having one input node, you will be having one output node, and number of summers will become number of nodes there, and the number of takeoff points will become number of nodes again there. Okay, so we'll see now. Okay, since we have input, we have one node, and for summer we have a node, and again here we have a summer, we have a node, and again here we have a summer, we have a node, and takeoff point, a node, and here a takeoff point, and also the output node we have here. It's got merged in this case, so we have altogether one single node. Okay, so I repeat once again, how many nodes you're supposed to take. So the number of summer plus number of takeoff point and input output node, input and output, all these things together gives us the number of nodes. So we have taken here. Okay, so here you can see that the takeoff point and the output node, they have merged, or else we can have a unity path and we can have an output node. There is no issue in that. So usually output node here, it's got merged. It can happen sometime, or else we can elaborately take a separate node for the output node from the takeoff point. But for a takeoff point, it is an essential, it is essential to have a node, and for a summer, it is essential to have a node, and input and output node is optional. I can merge here. See, for example, I have a input node. I can merge that to this summer node. I can do that. And similarly here, output node, I can merge to this last takeoff point what we have. So we can do input output merging. Otherwise, we can have one input node, one output node, and number of summer and number of takeoff points. So this many nodes will be having. Okay, so we have taken here an input node, we have an output, or as I said, it got merged with the takeoff point, and number of summers are 3, we have 3 nodes, and takeoff point here 2, we have 2 nodes for that. Okay, so now we have to connect these nodes based on the given block diagram. See here, from input to this summer, no gain is mentioned, so you have to take a unity path and you have to connect those two things. And from this summer to this summer, we have a G1, so that we have to draw it here. We have to connect this node with the block gain of G1. Okay, similarly from this node to this node we have G2, correct? So we have G2 here. Okay, and from this node to this node, what we have minus H1, and from this node to this node we have G3, and from this node to this node we have G4, and from this node to this node we have H2, minus H2 I have taken, because here to the summer we have taken a polarity minus, whereas here at the node I cannot show the sign, so I will attach that to the path gain, or whatever the branch I have. For the branch gain, I'll be attaching minus. Similarly here, we have a connection between this last node to the first summer. for that path we have a gain of H3, and for that H3 also I have taken minus. Okay, what does it mean? To the summer, we can give the polarity. Here to the node I cannot give the polarity, so that minus I'll be taking to the branch gain and I'll be mentioning here. Is this clear? So what we have done, we have converted given block diagram to a signal flow graph. The connections and all, whatever is there in the block diagram, we have retained. Only here interesting part is how many nodes you have to take. I repeat, how many nodes you have to take. Input and output node is optional. You can merge that to the rest of the node. You can do that. Otherwise, number of summer and number of take-up points are the essential nodes you have to consider in a signal flow graph. So from the signal flow graph, it is very easy to get the transfer function, because we have a handy Mason's gain formula, and we know how to estimate the different parameter of that Mason's gain formula. So first is identification of forward path. Okay, so how many forward paths are there? Only one forward path. Only one forward path. From left to right, you can travel. That is from input node to the output node. You have only one possible way to reach. So we have only one forward path. That is what the P1 says here. Forward path gain G1, G2, G3, G4. Okay, and next, how many loops? How many loops there are? You can see that there is one loop here. And there is another loop, and this is the third loop. There are 3 loops here. Okay, L1, L2, L3 we call it as. There are 3 loops, and we have to find out the delta, because we have 3 loops and we don't have any non-touching loops. Consider here this as a loop, that is G2, G3 minus H2, and consider a loop, second loop, say for example G1, G2, G3, G4 and minus H3, and third loop is G3, G4 minus H1. All the 3 loops, you will find that they are dependent to each other, because they are sharing the common branch and nodes. So there is no 2 non-touching loops. So if there is no 2 non-touching loops, 3 non-touching loops will never exist. So the 3 individual loops gain we have to calculate, and we have to compute the delta. Here we have a delta equation which is equal to 1 minus according to the definition, but in all the 3 loops we have minus, we have got plus here, and the first loop we have taken G1, G2, G3, G4, H3. That is what the first term we have corresponding to first loop. G2, G3, H2 second loop. G2, G4, H1 third loop. So the minus what we have here for all the 3 loop gain, that I took it out, and I have here according to the formula I had minus, that minus with the loop gain minus, we have plus here. So delta we have computed, and forward path we have computed. And how to compute delta 1? To compute delta 1, you have to remove the first forward path in the graph. So if you remove the first forward graph, you will left out with nothing. When you don't have anything left out in the graph, you don't have any loops existing. Since no loop existing, the delta definition becomes 1, only 1. So we have delta 1 is equal to 1. So you have to substitute in Mason's gain formula, that is P1 delta 1 divided by delta that we have here. So this is what the transfer function of the given what we call block diagram. So block diagram, in the last class we have, in the previous sessions, we have seen how to arrive at the transfer function from the given block diagram. It was such a tedious procedures, hope you have observed. Reduction technique, block diagram reduction technique is a tedious one. In few cases, it is very, very tough to reduce the block diagram. Whereas signal flow graph is so handy, you see. Okay, only analysis part you have to do it. Then comes to substitution. Only 2 stages we have: analysis of the different parameter, and the next is Mason's gain formula substitution. Only 2 stage we will be arriving at the solution. See how simple it is. We have arrived at the transfer function. So we always say that compared to block diagram, signal flow graph is quite easy, because it is only identification and substitution. Next example. So again, we have here one more block diagram, and to this we have to write the what we call signal flow graph. So while identifying a signal flow graph, you have so many options. You can take all the nodes in a sequence. In one line you can have it, or so as to retain the block diagram pattern as it is, you can assume the nodes in the same pattern. Okay, 2 layers, 3 layers nodes, you can keep it, and you can interconnect those nodes so that you will be matching with the block diagram, that pictorial representation block diagram what we have, you can match. Actually, there is no condition as such. The nodes, you can take it in your fashion, in any fashion possible. There is no restriction for that, but we try to keep it so that the signal flow graph resembles the block diagram, so that it is easy to identify, is there any part or any branch, is there any missing thing, we can easily identify. So because of that we will have it. Otherwise, there is no condition that x1 y1 should be above x2 y2. No condition as such. You can have all the nodes in a line and you can draw the graph. That graph will look totally different. The graph will look totally different, though it carries the same behavior and properties, but the appearance of the graph changes according to the sequencing of node or patterns, positioning of the node, how you will take it. Okay, so here we are trying to retain the block diagram representation as it is. So we will see how many nodes we require. So all the summers will form a node, definitely. So I have first summer here, 1, 2, 3, 4. So 4 nodes we have because of the summer, and we will be having takeoff point. Here we have one takeoff point, 1, 2, 3. Okay, so there are 6 nodes essential, and input node, output node, we can merge to the neighboring nodes, but we have taken here explicitly input node, whereas output node we are merging to the takeoff point what we have here. Okay, the first summer corresponds to a summer here, and this summer we have here, and this summer we have here, and y1 takeoff point we have here, y2 takeoff point I have here, and what we call this output node, or the last takeoff point I can have it here. Okay, now we'll continue. Interconnecting the nodes, interconnection of the node. Okay, and you might have observed one thing, this takeoff point we have not taken a node. Okay, for this takeoff point we have not taken a node. Actually we can take it. So here what we have done is, to this summer we have merged. For this summer we have merged because there is no gain existing between this summer and this takeoff point. I repeat, from this summer to this takeoff point, there is no gain exist. Similarly, from this takeoff point to the next part of the graph, there is no gain mentioned. That case, you can merge a summer and a takeoff point. Okay, I repeat once again, this is not a essential takeoff point, we call it as. Why? Because so here there is no explicit gain of the line gain doesn't exist. Here there is no line gain exist. This is as good as coming out of the summer. It is as good as saying that summer has got 2 output lines. It is as good as saying that. So just to avoid the complexity of the graph, this minor simplification you can do it. As I said, merging input node with the last takeoff point. We have done it here. There is no point in taking 2 explicit node. We have merged. You can do that, or you can have it explicitly. It is not it's not going to affect your graph in any way. So we are trying to avoid having number of nodes. Only the essential nodes we will be considering it. So here what we found is it is as good as coming out of the summer. So we have just merged it. Else you can have a separate node and you can continue as such. The analysis of the signal flow graph will not change. Signal flow graph appearance may change because we are introducing one more node. You will get one more node here, and again you will be branching from that node. So here and there you can just have some simplification while transferring the given block diagram to signal flow graph. Okay, you can do that. So we have a signal flow graph now, and we have to now do the analysis. So to start with, what we do is forward path identification. So number of forward path. So we found that there are 4 forward path here. Okay, so all the 4 forward path has been identified here. Okay, so you can see that there is a forward path like this one, there is another like this. Okay, so third one is, I'll just trace like this. I have to go like this, come here and like this. Similarly, I can have the fourth one going here through G2, unity, G1, going back to C of S. Okay, I repeat once again, the first forward path, R of S to E of S, E of S to X, X1 actually it is, X1 to Y1 and C of S. That is first forward path. Second is R of S to E of S, E of S to X2, X2 to Y2, Y2 to C of S. Third one, R of S to E of S, E of S to X1, X1 to Y2, Y2 to, sorry, I repeat, R of S to E of S, E of S to X1, X1 to Y1, Y1 to X2, X2 to Y2, Y2 to C of S. Similarly, R of S to E of S to X2, X2 through G2, Y2, Y2 to X1, X1 to G1, sorry, X1 to Y1, Y1 to C of S. So these are all the different node traversal we do for the 4 different path identification. So all the 4 path gain we have written here. P1 is equal to minus 1 G1, minus 1 G1. P2 is equal to minus 1 G1 minus 1 G2. Okay, P3 1 G2 1, P4 1 G2 1, G1 1. Oh, as we have traced all the 4 forward path we have mentioned here. Okay, so wherever is minus, you please consider minus properly here. Minus 1 we have here, minus 1 we have here. Okay, so those 2 minus we have taken while identifying the forward path. Is there any other forward path? No. So for these 4 forward path, we have to calculate the delta. So before calculating these delta case, we have to find first delta. So what is delta? Delta is equal to 1 minus sum of individual loop gain plus sum of product of 2 non-touching loops, and so on. Like that, we'll be keep increasing the non-touching loop numbers, and we will end up with the maximum loops which are available in the graph. Okay, so now how many loops are there? Okay, how many loops are there, you have to identify. Okay, how many loops are there? How many loops are there? You have to just trace the number of loops here. Okay, and you have to find out the individual loop gains, and you have to find out 2 non-touching loops there. Okay, and you have to compute the delta. So all those steps I cannot repeat again. Computation of delta, you please repeat here. Identify all possible loops and substitute in the delta equation. You will be getting delta here, what we have mentioned. 1 plus 2 G2 plus 4 G1 G2. Okay, this is what the delta we have. Similarly, delta K calculations, which we have learned in the previous classes, that is, while calculating delta 1, you have to remove forward path 1 in the graph, retain rest of the graph, and compute delta. Similarly, how to compute delta 2? You have to remove forward path P2, retain rest part of the graph, and you have to calculate delta, that becomes delta 2. Similarly, delta 3 is the delta calculation, removing P3 in the graph, retaining the rest part of the graph, so on. Okay, so that is what we have to do it. So we have this final equation, just pk delta k divided by delta. For forward path we have to take it, in the denominator we have to take it delta. So this is what we have the final transfer function. This is what the final transfer function according to Mason's gain formula. Okay, next example. So we have to determine the transfer function. Okay, the block diagram is very sorry, I will just I'll just stop at this stage. I'll continue this with this in the next class. Thank you.